In this video, we are going to discuss what I call the conservative vector field theorem. So that's what I chose as the title of this video. The theorem itself is not necessarily called that, but this theorem is a theorem found in vector calculus, and it states the following. Let F be a vector field that is continuous on an open and connected region D. So F is a vector field that is continuous on an open and connected region D. Now, if the line integral of F along C is path independent in D, then F is conservative in D. Okay, which basically means that there exists a function F such that F is equal to the gradient of this function F. Okay, so we are going to look at the proof of this particular theorem. So what it states, it basically states that if the line integral of a vector field is path independent, then that implies that that vector field is conservative. That's what it basically states. So now we're going to go and prove this. So let's go ahead and prove this. We are going to do the proof in R2. Of course, you can do the proof in R3 if you want to, but for this particular video, we are going to do the proof in R2. Okay, so now let us draw the region D. So this is the Cartesian plane here. This is R2. So let's draw the region D. Okay, so that's the region D. Of course, the region D can have any type of shape, but for this proof, let this be our region D, and let's just denote it D. Okay, now I'm gonna look at points here. Let's look at specific points inside the region D. So we're gonna choose points here. So, and we'll discuss what these points mean. So let's start with the point AB. So let this be a point in D, AB, and let the next point be the point XY here in D. And also, we are going to need another point. We're going to need another point. We're going to call this point. Okay, we're going to call this point X1Y. So we've got 3 points that we have here inside of D that we're going to use. Okay, so let's discuss what these points actually mean. Okay, let's go ahead and discuss what these points actually mean. Okay, so we say the following. Say let AB and XY, let AB and XY be points. Let AB and XY be points in D. Okay, so let AB and XY be points in D. So these 2 points that we just indicated here inside of D in our sketch, these are 2 points that are in D. Okay, now let the third point, let X1Y be another point in D. Okay, so let X1Y be another point in D, such that X1 is less, let me write that again, X1 is less than X. Okay, so X1Y is another point in D such that X1 is less than X. And the line segment that joins the line segment that joins x1y and xy is horizontal, meaning of course that it's parallel to the x-axis. So it's horizontal, which means that it's parallel to the x-axis. So we basically let all of these things be. Okay, now so now we continue and we let C be a piecewise smooth curve. Let's see it be a piecewise smooth curve, that joins AB to XY. Okay, so C is a piecewise smooth curve that joins AB to XY. All right, that is C. Now also, we let C1 be part of C. So let C1 be part of C. Okay, let C1 be part of C. Okay, so C1 is part of this curve C, this piecewise smooth curve C, where C1 joins AB to X1Y. Okay, so let C1 be part of C. Let C1 be part of C, such that it joins. So let C1 be part of C such that it joins AB. Let me write the B again. Such that it joins AB to X1Y. So C1 is part of C and it joins AB to X1Y. Okay, so if we go to the sketch here, there, C1 basically looks like this. It joins AB to X1Y. That's C1. So this here would be C1. Okay, let me do that again. Let me write the C1 again. So this would be C1 here. Okay, so that's C1. And of course, now let's also look at this one. Let's let C2 be also part of C2 is also part of C. So let C2 be part of C such that let C2 be part of C such that it joins the point X1Y. But first, before we continue with that, let's go back. Let's say that again. We just have to specify something about C2. Okay, so C2, let C2 be part of C such that it's the line segment that joins the point X1Y. Okay, so C2 is the line segment that joins the point X1Y to the point XY. So C2 is that line segment. So now let's draw C2. Okay, let's draw C2 in our sketch here. So C2 is basically this line segment here. It joins X1Y to xy. And note again that this line segment C2, so this is C2 here. This line segment C2 is it's horizontal. Okay, C2 is horizontal. All right, meaning that it's parallel to the x-axis. So we chose it such that it's horizontal. So we basically chose our points such that C2 is parallel to the x-axis, meaning that it's horizontal. Okay, so that's basically what we have so far. So that's what we have so far in the proof. So now we're going to continue. So we have all of this so far in the proof. Now we're going to continue. Let's continue. So now what we want to do is we want to construct our potential function, our desired potential function. So that's what we do next. We now construct our desired potential function here. That's the thing we do now. Excuse me, I've got hay fever, so that's why my voice sounds like this. Sorry about that. So now let us construct our desired potential function. So we now construct our desired potential. We now construct our desired potential function. Okay. So now we construct our desired potential function. So we basically let f of xy, this is our potential function, let f of xy be equal to the line integral of f, okay, that's f dot dr, along C, okay, along C. So C obviously is our curve that we discussed over here. We discussed C. C joins AB to XY. Okay, so C is a piecewise smooth curve that joins AB to XY, as we discussed before. So now we basically construct our desired function as follows. Okay, we construct our desired potential function as follows. We let f of xy be equal to the line integral of f along C. Okay, so obviously this is equal to the following. This is the same as the line integral. It's the line integral along this curve, see, from AB all the way to xy. So we can write it like this also. We can write it in this way. Same thing. So this is the line integral along C from AB, that's the initial point, and to xy, which is the end point of our piecewise smooth curve C. So that's how we can write it. We can write it like this. Okay. But now also we can do the following. So this is also equal to the following. Since C is made up of C1 and C2, we can say that this is equal to the line integral along C1, okay, f dot dr plus the line integral along C2, f dot dr. So we can say this because this curve C is made up of these two curves, C1 and C2. So we can equate this to that. Now this is also we can write it like this. Remember, the vector field F is it's path independent. The line integral of F is path independent. Okay, so that's basically the main assumption. That's the first assumption of the proof. Okay, so the first assumption of the proof is that the line integral of F in D, in this region D, is path independent. Okay, so that's basically the first assumption of our proof, that the line integral of F within this region D is path independent. So that's what we have. So this line integrals we have here, the one along C1, along C2, these are path independent line integrals because the line integral of F in D is path independent. So these are path independent line integrals. So we can write the first one, which is along C1. We can write it as follows. So this goes from AB, because C1 connects AB with X1Y. So this goes from AB all the way to X1Y. So that's F dot dr plus the line integral, and this one goes from X1Y to XY. So this one goes there. It's F dot dr. So that's what we have basically. So this is basically what our potential function f of xy is equal to. Okay, so we basically construct this function. We write it as such. We write it as such, and we're going to use all of this in the proof. So now we're here. The next thing we do is we go ahead and we partially differentiate throughout this expression. Partially differentiate with respect to x. Now, this implies the following. It implies that the partial derivative of f with respect to x is equal to the following. So obviously we're going to partially differentiate with respect to x. We're going to partially differentiate each of these terms, okay, or each of these integrals. So we differentiate this one, the first one, which is from AB to xy. That's f dot dr. Okay, so this implies that the partial derivative of f with respect to x is equal to the partial derivative of x, the partial derivative with respect to x of this first integral, plus the partial derivative with respect to x of this one from xy. Sorry, let me go back. So let's go back. Let me just write this down again. This is point x1y, not xy. This is x1y all the way to xy. Okay, this is x1. We go from x1y to xy. That's f dot dr. So that's basically what we have if we partially differentiate throughout this expression here. But let's note something. Okay. Okay, wait. Okay, I also left out a 1 here. Let me go back. Okay, let me go back here. This is supposed to be 1 here. Okay, it's x1y. This one here. Let me just rub it out first. Wrap this out. Okay, remember that the first integral goes from AB all the way to x1y. So this is supposed to be x1y here. x1y, not xy. So it's x1y. Okay, now it's fine. So now when we look at this, we can see that in this integral here, this first integral here, we can see that this first integral is it's not a function of x. Okay, so if you look at this thing, because the limits of this integral, the points that we integrate from and to, they are not dependent on x. We've got AB, the first point is AB, and we integrate to x1y, not xy, x1y. So this will, the resulting function from this integral, from this first integral here, will not contain x. It'll not be a function of x. So the partial derivative of this integral with respect to x is then 0. So we can then go ahead and write 0 there. Okay. This is because the resulting function will not be a function of x. So the partial derivative of this integral with respect to x is then 0. So this is 0. Okay, plus the second integral. So we can just leave out the 0. Let's just leave out the 0. Let's omit the 0. We know it's 0. So we'll just write the partial with respect to x of the integral from x1y all the way to xy. Okay, f dot dr. Okay. All right, so here we are. So now we have this. Now the next thing we do here, okay, the next part of the proof, or the next thing we do here, Excuse the rain. It's raining where I am. It's raining, so if you can hear the sound of the rain, excuse that sound. Okay, but anyway, anyway. So now let's continue with the proof. So now we're here. Now we can see that the partial derivative of f with respect to x is equal to the partial derivative of this integral from x1y to xy, and of course we're partially differentiating with respect to x. So now we do the following. Let's write the vector field f. Let's write it in terms of let's write it as a position vector. Okay, and we can do this thing for a vector field in R2, because we're working in R2 here. We can write f as p. Of course, p is a function of xy, so we can write it as p in the I direction plus q in the j direction. So we can write it like this. We can write it in this form because it's a vector field. So we can write it as a position vector where p is a function of xy and q is also a function of xy. And when we do this, that will imply the following. It implies that our line integral, this line integral here, we can write it, of course, using this functions p and q. We can write this line integral in terms of p and q. Okay, we can do that. So therefore, we'll have the following: the partial of f with respect to x is equal to the following. It's equal to the partial with respect to x of the line integral, of course, from x1 y to xy, okay, of p, and this is p of xy dx plus q of xy dy. Okay, I don't like how I wrote it. It's a bit messy. Okay, let me just do that again. Let me write that again. It's a bit messy. I don't like how messy it is. So this is going to be the integral of p xy dx plus q xy dy. Okay, so we can write this like this. We can write this line integral of f in this form, in terms of p and q. All right. So obviously you should know how to write it in this form. I'm not gonna go through the process of writing it in this form, but you should know how to write it in this form. Okay. Anyway, now let's continue. So now we have this. Now we have to note something about dy. Okay, we have to note something about dy. We can go back to our sketch here, what we said about the line segment C2. Okay, and of course our integral here, this integral here, is from x1y to xy. That's basically the line segment C2. So this line integral is along C2. Okay, this is a line integral that's along C2. We integrate over C2. And C2, of course, we know that it is a line segment that is horizontal, meaning that it's parallel to the x-axis. So this means that along this line segment C2, y doesn't change. Y is constant along C2. Meaning that along this integral, okay, or for this integral, because C2 is horizontal, we have that dy is 0. Okay? We have that dy is 0. Okay, so let's state that. Let's write it here. So because C2 is horizontal, we have that dy is equal to 0. Because C2 is horizontal, we have that dy is equal to 0. Okay, so that basically implies now that the partial derivative of f with respect to x, okay, is equal to the partial derivative with respect to x of this line integral. Obviously we go from x1 y all the way to xy, and now because dy is 0, we only have p of xy dx. But because we want to avoid confusion here with the x's, because x is variable and also it's part of the limits of integration, so therefore we're going to just write, in place of x, we're going to put t. So we can write this as the partial derivative with respect to x of the integral from x1 y to xy. That's the limits of integration. And the function p, in place of x, we're going to put t here. Okay, just to avoid confusion. So this will be dt as well. So we integrate in that way. So the partial derivative with respect to x of such an integral, obviously, in any situation, if you're differentiating an integral, the result will be the integrand. It'll be the integrand, because integration is basically finding the function that you differentiate to get the integrand. So if you're differentiating the integral, your answer will be the integrand. So meaning that in this case, our answer is simply just p of xy. It's the function p. Okay, it's the function p. So the partial derivative of f with respect to x is equal to p of xy. All right, so that's what we've shown. That's the first part of this proof. The second part of this proof, we're going to do the following. We're going to show that the partial of f with respect to y is equal to q. So let's go ahead and do that. But before we do that, let's go back to the sketch over here. Okay. Now this is for the second part of the proof. So we're doing this for the second part of the proof. Okay. We are going to work with the same point. Keep AB, keep XY, and they are exactly the same points that we discussed before. Okay, we discussed what these points AB and XY are. It's basically just 2 points that are inside of D. These are 2 points that are inside of D. Okay, so this is what we're gonna do. Now let's rub out the curves, because we're not gonna use the same C1 and C2. We're not gonna use the same curves. We're gonna use the same 2 points, same initial and end point, and this is where the path independence of f comes in. Okay, this is where the path independence of the line integral of f rather comes in. So for the second part of the proof, we are going to use the same picture, okay, as we used before. We've got the same region D. We've got the same 2 points we started with, point AB and point XY. Okay, but we are going to use a different curve. We're going to use a different curve, but the line integrals though will be the same, because the initial point and the end point is the same as before. So you know, this is where the path independence comes in, the path independence of the line integral of f. Because we said that the line integral of f is path independent in D. That's the initial assumption of our proof. The line integral of f is path independent in D. Okay? So therefore, if you got two different curves that join AB to XY, the line integral of f along those 2 curves is going to be the same. All right, so that's basically path independence. So now, for the second part of the proof, then, we do the following. We choose another point. Okay, we have a different point, third point. Okay, so we choose this point, and we call this point, we call it, okay, we choose a third point. Okay, so meaning basically in addition to the points we started with, which is A, B, and XY, we choose a third point, similar to what we did before. And this third point, we're going to call this third point, we're going to call it XY1. Okay, so this third point is called XY1. Okay, and then let's state the following. We're going to come back to that sketch there. But before we go to that sketch, we're gonna state the following. Let's state this. Okay, let's state this. We're gonna say, let XY1 be another point Okay, let xy1 be another point in D such that, so let xy1 be another point in D such that y1 is less than y, and the line segment that joins xy1 to xy is vertical, meaning that it's parallel to the y-axis now. Okay, so the line segment that joins x y1 to x y is vertical, which of course means that it's parallel to the y-axis. So we let this be the case. We let this be so. And again, we let this be the case. So we let B be a piecewise smooth curve. So now we have a different curve now. We have B. Let B be a piecewise smooth curve. Let B be a piecewise smooth curve that joins AB to XY. So B is a piecewise smooth curve that joins AB to XY. So let B be a piecewise smooth curve that joins AB to XY. And also let B1 be part of B. Okay, let B1 be part of B. Let B1 be part of B such that it joins, be part of B such that it joins AB to XY1. Okay, right? So B1 is part of B and it joins AB to XY1. So meaning that this is B1 here. Okay, if I had to sketch B1, I have the following. So if I'm sketching B1, then I have this. This is B1 here. So B1 joins, and it's not necessarily a line segment, it's just a curve. So B1 is just a curve. I can draw it like this, make it curved a bit. So this over here is B1. Okay, not B2, sorry, B1. Let me put 1 here, sorry. That's B1. So B1 joins AB to XY1. And what about this? Okay, all right, okay, that's fine. So B1 joins AB to XY1. So B1 is part of B and it joins AB to XY1. Now we let B2 be part of B. Let B2 be part of B such that it joins. So B2 is part of B. B2 is part of B such that it joins XY1 to XY. Okay, so that's B2. So B1 joins AB to XY1 and B2 joins XY1 to XY. But note that B2 is a line segment, so we have to specify that. So B2 is part of B such that it joins XY1 to XY, and it's a line segment. It's a line segment. So maybe I should rewrite that. Let me write that again, just to specify that it is a line. It's a line. It's a straight line segment. So B2 is part of B such that it is the line segment. Let me say it is the line segment that joins those 2 points, just to specify that it's a straight line, such that it's a line segment It's a line segment that joins xy1 to xy. So that's basically that's B2. And of course we can go here and sketch this curve B2. So B2 is really a straight line that joins those 2 points there. Okay, that's B2. So B2 is specifically a straight line. That's B2. It's a vertical straight line, basically. All right, that's B2. So we got B1 and B2. And obviously, they make up the curve B, right? They make up the curve B. So B1 and B2 make up B. They make up the curve B. The whole curve is B. I can also denote B here, but you know it is, okay? So we can just leave it like that. We can leave it like that, and let's go back to our discussion here. Okay, so now we continue. Now we are going to look at our potential function, and we are going to use the same potential function that we used before in the first part of the proof, because it has to be the same. We can't change it. It has to be the same one. But we are going to now write the potential function, same potential function, but now we're going to write it in terms of the new curve B. Okay, it's a new curve, but it gives us the same potential function because of the path independence of the line integral of f here in D. So we have already constructed our desired potential function. Okay, we've already constructed our desired potential function f, okay, as follows. Okay, as follows. So we wrote it as, we said f of xy is the line integral along C of f. Okay, so this is how we constructed it. And of course, we know that this is a line integral. The line integral along C is obviously the line integral from AB to xy along the curve C. So we wrote it like this. So this is how we wrote it before. Okay, this is how we wrote it before. But then this is the same as this because of the path independence of the line integral of f. This line integral is the same as the line integral along B of the same vector field. Same line integral. They are equal because it's path independent. Okay, so basically this is still the same potential function that we had before, but now we can write it in terms of B, which is of course B is a new curve. It's a different curve from the curve C, but it gives the same result because of the path independence of the line integral of f in the region D. Okay, so we still use the same potential function. Okay, so there's our potential function. Now we continue. Okay, now because B is expressed, okay, B is we said B is a piecewise smooth curve that joins AB to xy, and we wrote B in terms of two other curves. That's B1 and B2. Okay, if you look at the sketch there, we've got B1 and B2, and B1 and B2 make up B. Okay, so this means that this integral here is the same as the integral along B1 of f, that's dot dr, plus the line integral along B2 of f dot dr. It's the same as this. Okay, so this integral is the same as this. We can write it like this, and obviously this is equal to the line integral. I mean, the one along B1 is we go from AB all the way to x y1 f f dot dr plus integral plus the integral from x y1 to xy of f dot dr. Okay, so we can write it like this. And then, as you can see, this is now similar to what we had before in the first part of the theorem. We can now go ahead and differentiate throughout, but now we're going to differentiate f with respect to y now. So let's differentiate f with respect to y. Okay, differentiate with respect to y. So now we're going to differentiate this integral here. We've got f dot dr plus the partial derivative with respect to y of the integral from x y1 to xy of f dot dr. So now, if you look here, if you look at the first integral here, you can see that the resulting integral here, the resulting function from integrating this, will not be a function of y, because you integrate from ab to xy1, not y. So the resulting integral will not be a function of y. So which makes this integral here equal to 0. No, not the integral, which makes the derivative, which makes the derivative, the partial derivative of this integral with respect to y equals 0. Okay? So now this implies the following. This implies that the partial derivative of f with respect to y is equal to the partial derivative with respect to y of the line integral of x y1 all the way to xy f dot dr. So there we go. So now we have this over here, and we've already written f. Okay, so in the first part of the proof, we already wrote f in terms of p and q. Let's go back to that over here. F is equal to pi plus qi. So now we're going to use that in the proof, and we're going to write our integral here in terms of that. Okay, so this is equal to the partial derivative with respect to y of the line integral from xy1 to xy of p xy dx plus q xy dy. Okay, now again we remember this, the line segment, because this integral is the integral from xy1 to xy, basically is the integral along the line segment b2, and the line segment b2 is vertical. So therefore, which means that dx is 0, because x doesn't change along that line segment. So we're going to say because b2 is vertical, meaning parallel to the y-axis, because b2 is vertical, we have that. Okay, because b2 is vertical, we have that dx is equal to 0. Okay, now obviously that implies the following. That implies that the partial derivative of f with respect to y is equal to the partial derivative with respect to y of the line integral from xy1 to xy of q of xy dy. Now, to prevent confusion, we can write the variable y in terms of t in the integral, so that we don't confuse the what we have in the integrand and what we have in the limits there. So we're going to go from x y1 all the way to xt. Sorry, that's xy. This should be y over here. We should write the t inside the integrand. So we got x here, we put t here, and we put t here also. Okay, so we can do that. And of course, again, the integral here differentiating it with respect to y, and you differentiate this integral, you are going to get the integrand. So this will give us qxy. Okay? Now, we have the following. So now we've shown, so therefore, we've shown that, okay, we've shown that the partial of f with respect to x is equal to p, okay, and the partial of f with respect to y is equal to q. We've shown that, which basically implies the following. It implies that f, the vector field f, is then equal to the partial of f, because that's how we wrote it, okay? F is equal to the partial of f with respect to x in the I direction, because p is equal to the partial of f with respect to x. So we just replace the p with this partial derivative, plus the partial of f. Let me just write that again, sorry. Write that again. This is the partial of f with respect to y in the j direction. So obviously this over here is the same as the partial with respect to x, the partial with respect to y, okay, multiplied by this f over here. All right, so it's basically the same thing as the gradient vector, and you basically multiply f into the gradient vector. It's the same as this, which of course implies that f is conservative. This implies that f is conservative, which then completes our proof.